This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Welcome to our Distinguished Lecturer Webinar Series. My name is Carrie Cosby, and I'm the Chapters Manager at the IEEE Computer Society. I oversee our more than 500 professional and student chapters around the world and manage our Distinguished Visitors Program. I'd like to take care of some housekeeping tasks. You can ask your questions in the Q&A panel. Then Dr. Sengupta will answer as many questions as possible following the presentation. When you're writing your questions, if they pertain to a particular slide, please make a reference to that slide so that we can come back to it when we're answering the question. The webinar is being recorded, and the slides and recording will be made available after the webinar. Today's discussion is digital signature and IP steganography for securing hardware accelerators. I'd like to introduce our speaker. Dr. Sengupta is an associate professor in computer science and engineering at the Indian Institute of Technology, Indore. He holds a PhD and MA Sci in electrical and computer engineering from Ryerson University in Toronto, and is a registered professional engineer in Ontario. He's a fellow of the IET and fellow of the British Computer Society in UK. He's an IEEE Distinguished Visitor, IEEE Distinguished Lecturer of the IEEE Computer Electronics Society, and the IEEE Distinguished Visitor of the Computer Society. He's the recipient of prominent awards and prizes, such as the IEEE Chester Saul Memorial Consumer and Electronics Award, the IEEE Outstanding Editor Award from the IEEE Consumer Technology Society, IEEE Best Research Award of the IEEE Consumer Technology Society, IEEE Best Paper Award of the IEEE Consumer Electronics Society, the IEEE Outstanding Associate Editor Award of the IEEE Computer Society, IEEE Best Paper Award of the IEEE Computer Society, TC VLSI, etc. He has over 240 publications, including 4 books and 11 patents. Dr. Sengupta, I'd like to pass the floor to you.
Thanks a lot, Kerry. It's a privilege to be giving a lecture as part of the IEEE Computer Society Distinguished Lecture Series. I would like to welcome all the people out there for my talk today. Okay, so the title and topic of my talk today is on digital signature and IP steganography for securing hardware accelerators. Before we actually start with the talk, I would like to give some basic background on what this area is all about, and then we can just get into the topic of the technical contents. So this area actually focuses on the protection and security of IP cores. IP cores as in like the reusable intellectual property cores, which are often an integral part of the system on chips, and they often play a very vital role in designing of consumer electronics products. So, for example, if I take an example of a digital camera, you see, like simply converting an analog image that is captured by the CCD into its digital data does not actually create a digital data, okay? So the role is CCD is limited only to converting an analog image into its digital counterpart, which we call as raw data. But the actual processing of the image happens right after that. So when it passes and processes the image through image processing engine and something known as a compression engine like JPEG, which is where the role of hardware accelerators come into the picture. So these are the real hardware accelerators that I'm talking about in the context of real commercial applications like digital camera. Okay, so for example, in case of image processing, an example could be brightness adjustment, sharpness adjustment, contrast adjustment, and so on. When I'm talking of the compression, I'm really talking of how you can compress an image, okay, into its respective compressed format, which is a JPEG format, using hardware, and that hardware would be a dedicated hardware accelerator that is responsible for only performing compression. Okay. Some other examples that I could think of is, for example, some DSP cores that are often widely used in several applications, such as digital IR Butterworth filter, FIR filter, discrete cosine transformation, inverse discrete cosine transformation, fast Fourier transform algorithm, low-pass filters, high-pass filters, JPEG compression, decompression like JPEG codecs, which I was just talking about, hard wavelet transformation for image compression, and so on. So as you will see, there are several examples of hardware accelerators in the domain of digital signal processing and image processing and multimedia, which are widely used in different devices. Okay, so all what I'm just trying to say basically is that
this is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
Okay, I think we had a small glitch in between. Anyway, so we'll just go directly into the content. So as I was saying that, we are talking about different type of DSP cores, and these DSP cores, which are the examples of hardware accelerators that play a vital role in different consumer electronic products and several other systems. So the goal here is how to protect and how to secure these systems against cyber attacks and state-of-the-art cyber threats. Okay, so that is the main topic and focus of today's webinar. Okay, so DSP and multimedia-based reusable IP cores form the key components of SoCs in consumer electronic devices, and as we know that these devices are involved in the global design supply chain process, so which makes it very vulnerable to security threats such as IP cloning, IC cloning, false claim of ownership, and so on. So I would like to specifically discuss two major branches of IP core protection. First is known as digital signature, and second is known as IP steganography, that is used and quite effective in securing IP cores. So before I go into that, let me talk a little bit on the hardware threats. So IP cores are susceptible to hardware threats of IP counterfeiting and IP cloning. Okay. There's a small technical difference between the word counterfeiting and cloning, which I'll talk about in the upcoming slides. But it's important that an hardware needs to be secured against counterfeited and cloned versions. And these threats have emerged due to the globalization of the design supply chain. And important and very interestingly and importantly that this is such a critical threat that needs to be secured because they can sabotage the reputation of a genuine IP vendor and can also cause huge revenue losses. So both digital signature and IP core steganography can actually help in providing forensic detective control against such threats of IP counterfeiting and IP cloning. Okay, by implanting a robust, invisible, secret mark as a digital evidence into your DSP cores or into your hardware accelerators, which could be a reusable IP core as well. Okay, so some of the contemporary approaches that have been worked on by different researchers across the globe would be, for example, employing watermarking using true or multivariable auxo signature. Okay, so there are different designers specified encoding rule for each signature variable that needs to be converted into its respective signature constraints that gets implanted into the device. And the security of these approaches are intact as long as the signature and encoding are not compromised or leaked by an attacker. So that's a very important point. But once both are compromised, then the vendor fails to prove his or her IP ownership and detect the IP cloning or counterfeiting process. Okay, so let me first talk about the basics of what is a crypto digital signature approach. So it basically comprises of crypto hash functions, which is known as SHA-512. SHA stands for Secure Hashing Algorithm. And it also comprises of other security modules such as crypto encryption function like RSA. It also comprises of several layers of encoding. Okay, that are either part of the pre-processing or post-processing of the entire flow. And we'll talk about that in the next slides. And the generic steps of generating a digital signature would basically include a bitstream representation of the DSP followed by performing SHA-512, post-processing step number 1, RSA encryption and post-processing step number 2. So we basically have two post-processing and we have the bitstream representation in the form of an encoding algorithm. Then we have the SHA-512 and then we have the RSA encryption. So these are the major steps that are involved in generating a digital signature that could act as an invisible secret constraints or invisible artificial constraints for your hardware device. Okay. Now let me get into the details of this approach. So you start basically with the DFG of the DSP application. So DFG is a data flow graph. So this could be an intermediate representation of a C code, or it could be an intermediate representation of a VHDL code. So basically we need to, or we can directly feed a C code as well into the application if it's a tool. But we start with either a C code or an intermediate representation along with the resource configuration. And this resource configuration could be user specified, or this could be obtained from, design space exploration process, which is part of a high-level synthesis framework. In the pre-processing block, we construct the scheduled graph of that and we assign storage variables. And in the encoding rule number 1, we generate the bit stream from that using an encoding algorithm. After the encoding algorithm, then we perform SHA-512 to convert that respective, input bit stream into its digest form, which is usually, 512 bits, and the input is 1024 bits. This output, which is 512 bits, is then subjected to post-processing block number 1, which is responsible for dividing the bit stream digest into M blocks of size n bits, and then converting each of these n bit block into its respective decimal form. Each of these decimal chunks that we have got of n bit, which is typically 120 bits that I'm talking about, is then sent into an RSA encryption block, which encrypts each decimal value using RSA encryption algorithm. Here, RSA encryption algorithm works under the influence of a RSA private key. Unlike in normal encryption where you have a public key and then you have decryption done through the private key, it's just the opposite. You are actually digitally signing the digest using an RSA private key. So we do it using a private key in case of encryption here. Then you have the post-processing block number 2, which constructs a final bit stream from the encrypted decimal value, and then you have the encoding rule number 2, which actually encodes the bit value of the encrypted bit stream. And finally, then it embeds the digital signature in the register allocation phase of the high-level synthesis framework, And finally, you get the digital signature, which is embedded, okay, in the DSP design. So that's what I'm basically talking about. Having this, the combination of few layers of encoding, then you have the combination of the SHA-512, then you have RSA encryption, and you also have something known as truncation of the bit streams, which I'll talk about when we go to the examples of this. Okay, so let's move forward. Okay, so in this, what I'm going to talk about is basically, two major properties which are part of the SHA-512. The first is, the first property is known as collision resistance. This collision resistance is a very important property in SHA security module or SHA 512 security module, which basically states that two inputs can never have the same, hash digest. And then the next property is known as deterministic property, which also states that for every same input will produce the same, hash digest. Okay. So therefore, these two properties ensure that the generated hash digest carrying the vendor's secret mark is unique for an IP core design. Okay. So it is not possible to replicate it basically. Okay, now let me also give an example of RSA encryption. So as we know, RSA is an asymmetric key encryption algorithm in which two distinct keys, public and private, are involved in the cryptography process. And it is actually used to sign the hash digest of the vendor's secret mark information to ensure authenticity of the genuine owner. Okay, so only the IP vendor would know what is the actual secret value of the private key, which he has used to digitally sign the hash, okay? And that private key information or value is actually used to generate the digital signature value. So for example, this input 120 bit of an RSA algorithm is shown on the first two columns, or rather the first column, and then you have the output in the second column, and its binary equivalent is shown in the third column. So the input is 120 bit and the output is also 120 bit. So typically it will be, if it's a 512, bit output, it will be 4 chunks, each of 120 bit, which will be fed into the RSA encryption algorithm. Okay, in the post-processing block number 2, the encrypted decimal values, which is the output of the RSA module, are provided as an input to the post-processing block number 2. And each decimal value is converted to binary, and these individual binary streams are concatenated to form a single, bit stream value. Okay, so the point of concatenation is very critical, and only the authentic and original IP vendor will have information on the points of concatenation. Okay, so in case he needs to prove his ownership, he can actually use that information, secret information on the points of concatenation to decrypt. Okay, and get to the same hash value, which could be verified by performing the second hash. Okay, so if the second hash or the recomputed hash matches with the decrypted hash, okay, which could only be done by the original vendor or authentic IP owner, because he knows the point of the concatenation, he can easily or seamlessly prove his IP ownership compared to an imposter. Okay, so basically this concatenation of the bit streams which are performed, they will give you the final digital signature. Now let us talk a little bit about the embedding process of the digital signature. Okay, so embedding process of a digital signature can be performed, okay, using the following encoding rule. So you may have bit 0, which is used for signifying that an artificial additional edge needs to be added between the prime node pairs of a colored interval graph. So colored interval graph is a representation of the register allocation phase of high-level synthesis. So adding an edge between the two nodes means they cannot be executed by the same register. So they must have different color and they have to have different register allocations. Bit 1 represents that an artificial edge is added between even node pairs in the CIG or colored interval graph. Okay, so these two different forms of artificial edges are added into the CIG of the respective DSP design in order to implant the secret constraints. And finally, these constraints could act as a watermark in the register allocation step during HLS. And these hidden constraints are acting as additional constraints which are imposed on the design besides the regular design constraints that exists. Okay, so let us talk a little bit on the digital signature detection process. So how do you detect a digital signature once it's implanted? Because it needs to be verified also, right, in order to prove the ownership. So first step is to inspect the RTL data path of the IP core design under test, and it's inspected to collect the information of the storage variables. And once these storage variables are collected, then it is subjected to signature verification. But the question is, how do you collect the storage variables? To do so, basically, the inputs of all the muxes that are associated to each registers are inspected, and this inspection provides information of the register allocation of all the storage variables. So basically, you have to look for the input of the multiplexers corresponding to each of the registers that are part of the RTL data path. Okay, and RTL data path is the output of high-level synthesis, basically, that I'm talking about. And once this is collected, then in the signature verification process, the objective is to verify the presence of the digital signature in the collected information from the preceding step, okay? And this is done by verifying the register multiplexer inputs to the data path to check if they match with the digital signature value. Okay, now let me talk a little bit on one of the motivational examples that I've put here in order to show you, okay, how it works. So let's say this is an 8-point DCT code, which is a very important part of the JPEG compression process used in most of the camera systems. So the generic equation is shown here on inside the green colored box, and the corresponding data flow graph of it has been extracted and derived. And the resource configuration that has been obtained as a part of the design space exploration process is 3 multipliers and 1 adder. Okay, and we will use this information of 3 multipliers and 1 adder to actually schedule this graph and then obtain its respective bit stream, okay, based on an encoding rule. So let's have a look how to do that. Okay, so you have the bit stream, okay, which is shown on the, for example, which is shown on the right side, and you have the scheduled DFG on the right side, which is divided into control step number 0 to control step number 8, and the corresponding bitstream representation is shown on the left side. So since there are 15 operations, so there will be 15 generated bits, because every operation and its combination with the control step has been encoded into its respective binary bit. For example, if the operation number and control step number both are of the same parity, that is both are odd, then a bitstream generated is 0. If they both do not have the same parity, then the bitstream generated is 1. So therefore, for operation number 1 and control step number 1, the bitstream generated is 0, while for operation number 2 and control step number 1, the bitstream generated is 1. So on. So you can follow, for example, the simple rule of encoding to convert your scheduled data flow graph of a DSP application like 8-point DCT into its respective bitstream representation, where the size of the bitstream representation will be exactly equal to the number of operations in the data flow graph, okay, that you are taking into account. Okay, now let me talk a little bit on how to actually convert that binary bitstream representation into its corresponding additional edges. So for example, if you have a bitstream of 0, 1, 1, 1, so on till 1, 1, then you perform hashing using SHA-512 and generate the 512-bit hash digest, which is further divided into m chunks of n bits, and then you employ the RS encryption of each of these decimal equivalents of this n-bit chunk, which is used on, performed using private key of the RSA, followed by concatenation of the encrypted bits, and finally the encrypted bit stream, which is used for generating the digital signature post truncation. So for example, you have this 15 bits or 15 digits, for example, for s equals to 15. The corresponding edges would be, you would have to convert this bit stream of 1 and 0 to its equivalent pairing based on the encoding rule, which I had discussed in a few of the slides back. For example, the encoding rule 1 would mean that you would have to insert an additional edge between even pairs into CIG. Having a bit stream as 0 in a bit stream would mean to have a even odd pairing in the CIG, and so on. Okay, so for example, that's why we have this 2, 4, for bit stream number 1, then we have 2, 3 for bit stream number 2, then followed by the next 0 will have 2, 5. Okay, so it's basically doing a pairing between prime numbers of the storage variables, and 1 is doing a pairing between the even storage variable pairings. So on, we can actually generate the corresponding additional edges inside the CIG of the respective DSP design. So this is how the colored interval graph will look like. For example, you will have, for example, these nodes are actually referring to the different storage variables, and the colors inside the nodes are actually referring to the registers types. For example, this is a blue register, this is a red register, and so on. And the abbreviation of these registers are shown on the table on the right side. So for example, if this is the corresponding additional edges that you have derived based on the bit stream, so it basically says that there cannot be a same allocation to a register of storage variable V2, V4. So if you see the pre-embedding, then you see V2, V4 are anyways by default allocated to different registers R and G. Okay, then you have 2, 3. Okay, 2, 3 are anyways part of the red colored register that needs to be changed. So therefore, in the post-embedding, we will actually employ this external constraint to change the allocation of V2, V3 by local alteration. So V2, V3 now you see in the post-embedding table do not have allocation to red. Okay, so V2 is allocated to red and V3 is allocated to blue. Okay, so you've actually done some local swapping of the storage variables in order to accommodate the constraints that you've got as a result of the additional edges. So this is exactly what I'm talking about, that you can keep doing this until all the corresponding additional edges, which are part of this table, are in fact accommodated completely into this colored interval graph table that you see here. Okay, so this is pre-embedding, and after you perform or embed all these additional edges, this is a post-embedding table that is visible. Okay, now let me talk about the design cost of the different DSP applications that we have evaluated through the experimental results. So for example, we have tested these applications on JPEG IDCT, BPF, JPEG downsample, matrix multiplication, ARF, and so on. So as you could see here that, based on the digital signature size, the cost initially increases to a small extent, and then it becomes, same. Okay, it doesn't basically change either. Neither does it go high nor does it come down. So it remains constant basically. So this graph reflects that the change in cost is very minimal. Okay, with respect to the change in the digital signature strength. So even for a very high digital signature or a very robust, strong digital signature, such as S equals to 60 or S equals to 120, the cost of the respective DSP application is not different. This slide basically talks of how to evaluate the robustness, of your algorithm or of your method using something known as probability of coincidence metric. So this basically tells you that what is the probability of finding a watermark or a digital signature implanted constraint in a non-watermark or a baseline design. Okay, so what is the probability of doing it? So the lower the probability, the more robust the algorithm is considered to be. So as you could see that for sizes S15 to S240, the PC value decreases as you keep on increasing the size of the digital signature. And this is because you are actually adding more number of artificial, invisible additional constraints into your design that are playing a key role in enhancing the digital evidence of your application. So graphical comparison, with one of the state-of-the-art approaches, on hardware watermarking has revealed that there is a significant percentage reduction in PC value, which indicates that it actually provides a stronger proof of IP ownership, compared to the hardware watermarking approach. And this the value is, equally strong, and the percentage reduction is equally great for all the values, whether it's S15, S30, S60, and so on. Of course, for some applications like DWT ARF, there is no change because it doesn't have the capacity to accommodate so many constraints. Okay, now I'll move to the second half of my talk. So this will focus on a new topic which is known as securing IP cores in C systems using key-driven hash chaining-based steganography. So it's basically talking of signature-free mechanism where you can implant a digital evidence into your design without the involvement of any signature. Okay, so it uses a process of key-driven hash chaining, and the key points of this is that it uses a novel encoding algorithm, and it uses a novel key-driven hash chaining process for generating the invisible signature-free stego-constraints, and these are implanted into the design during dual phase of high-level synthesis process of a hardware accelerator design. So how do we detect the fake IP ICs using proposed steganography? How do you detect it? So for example, if you have a brand X IC, and that brand X IC, if you can extract the stego mark from a brand X IC and you can match the stego mark, so you can see that if the stego mark exists, so it's probably not a counterfeit. If the stego mark does not exist, it is probably a counterfeit. In case of cloning, it's a brand Y that contains the stego mark. If that is so, that is a different brand that contains the stego mark of brand X, then certainly it's a copy of an IP. If it does not, then probably it is not a copy of an IP. So that's how an invisible stego mark post-extraction can actually help you to detect an IP counterfeiting, an IP cloning, or basically a cloned or a counterfeited version of the actual IP. So this is the design flow of an IP steganography process. So you have the stego-keys, the resource constraints, the DSP application in the form of DFG, which is very similar to what we had spoken about in case of digital signature. Then we have the module library. It is then subjected to scheduling, allocation, and binding process, followed by scheduled and resource allocated DFG, which is generated as an output. And from that, then we again employ some encoding algorithm to produce a bitstream representation of the respective DSP application. And then you employ the stego-constraint generation process using the key-driven hash chaining algorithm that produces the stego-constraints, which are then further implanted during the FU allocation and register allocation process of a high-level synthesis. And finally, what you have is a stego-embedded DSP core, which can provide detective control against IP counterfeiting, cloning, as well as fraudulent claim of IP ownership. Okay, so this actually talks about the entire process in more details. So I'll go gradually, into this. So you have the DSP application, which is a scheduled DFG, and from there are a number of encoding algorithms that could be used to derive the M-bit bitstream representation of the respective DSP application. So therefore, we have encoding E1 to encoding En, because there are possible 2 to the power m number of encoding algorithms that are available or possible, okay, to generate an n-bit representation of the respective DSP application. And each of those m-bit representation will act as an input to the to the n:1 multiplexer, and we will have these n number of encoding outputs being fed as the inputs to the n:1 multiplexer, which are controlled by the stego key 1 to stego key n, because we have this n number of multiplexers also, okay, that will have this n number of encoding algorithms as an input, and therefore we have n number of stego keys from stego key 1 to stego key n, okay. And we also have two different types of hash blocks. One we have as a regular hash block, second is a key-driven hash block. So the regular hash block is from hash block number 1 to hash block number n, and the key-driven hash block is from hash block n+1 to hash block twice n. Okay. In the first step, in the first hash block, it is a pre-processing, which is done in order to produce a 1024-bit information as an input, and the hash block produces a 512-bit output. And along with the 380-bit information which comes from the bit padding block, okay, and this 512-bit, plus we have something like 1000-bit which is added before the 380-bit output, followed by appending 128-bit representation of the length 512 from the previous block. We will again produce an input to the hash block 2, which is 1024-bit, which again produces the respective 512-bit block output, okay. And the same process gets repeated till you come to hash block number twice n. The only difference is in case of hash block number twice n, okay, the bit padding information is coming from the output of the multiplexers, where in case of the regular hash blocks, the input of the hash block was coming directly from the output of the bit padding, where bit padding was not controlled through the multiplexer or through the stego keys of the multiplexer. It was directly coming from the respective encoding algorithm. So that is the difference between having a regular hash block and a key-driven hash block that you see here. And once the 2n number of hash blocks have been traversed, then it produces the bit stream, which is 512 bits, which is subjected further to truncation based on the designer's selected constraint size. And then whatever is the value of the bit stream, truncated bit stream, that is then converted into its respective stego constraints based on the encoding rule. Okay, for example, you may have an encoding rule for bit number 0, and you may have an encoding rule for bit number 1. Okay, and based on that, for example, you may produce the stego embedded DSP code. And this bit 0 and bit 1 would in fact refer to implanting artificial constraints at the register allocation phase of ESL synthesis or HLS, or bit number 1 could be implanting artificial constraints during the FU allocation or resource allocation phase of high-level synthesis or ESL synthesis. Okay, so that's how this process of IP core steganography in details work. Okay, I'll do one example to make it more clearer. So I was talking about having n number of encoding algorithms or rules that could produce m-bit output based on the DSP application. So some of the examples of those encoding algorithms are shown in this slide. For example, encoding algorithm even would mean that if the operation number and the corresponding control step number are both even, then we have a 0. Otherwise, it's a 1. Encoding rule number 2 states that if the operation number and the corresponding control step number are of the same parity, then it's a 0. Else, it's a 1. E3 states that if operation number and the corresponding control step number both are odd, then it's a 0, else it's a 1, and so on. So you may have these, different types of encoding algorithms that could be devised by the designer, and they could extend up to 2 to the power m number of different types of encoding algorithms possible for a m operation data flow graph. Okay, so therefore these are just some examples that I've listed out here for you to understand that how the encoding rule basically works for the operations of a DFG. Now this could be, for example, if I take an encoding algorithm rule number 1, which says if the operation number and the corresponding control step number are both even, so it's a 0, and otherwise it's a 1. So based on the encoding rule that I have used here, or used as an example, I can convert this respective graph that you see here, which is of an 8-point discrete cosine transform, into its respective encoded bit stream, as you see right at the bottom of your screen, which is 1 1 1 1 till you have the last 4 digits as 1 1. So you have this stream number, I think it's 1 2 3 4 5 6, stream number 6 and 8. Okay, at position 6 and 8, it's basically a 0, because the reason is because both the operation number and the control step number are even in this case. Okay, so if you see the operation number 6, it is assigned to an even control step, and the same thing happens with operation number 8, which is also assigned to an even control step. So therefore, for operation number 6 and operation number 8, it's a 0. Okay, that has been derived as an encoded output. So that's how an encoded bit stream could be easily generated for any DSP application that you take into account when you want to secure your hardware accelerator. Now, as I said, once you have this encoded n bit streams, then you can actually use this stego key to have this proposed hash chaining to produce a final hash output, and then it could be subjected to truncation by the designer. For example, a designer selected size could be s equals to 24, and then based on the conversion rules, which I said that you could have for 0 and 1, the respective edge constraints could be generated. So if it's an edge that is added between the even node pairs, so the edges would be S0, S2, S0, S4, S0, S6 till you go on until you have S2, S6. And for the FU allocation, it would be operation number 1 assigned to the hardware of vendor type 1, operation number 2 assigned to hardware of vendor type 2, so on till you have operation number 11 assigned to hardware of vendor type 1. Because the rule states that the odd operations are assigned to the FU of vendor type 1 and the even operations are assigned to the FU of vendor type 2. So using such encoding rules, okay, for the bit streams, you can generate the edge constraints and the corresponding stego constraints for the FU allocation phase of an HLS process. So this graph is just showing the interconnectivity information amongst the different storage variables, okay, in a colored interval graph. And as you could see that the red dotted lines are basically showing the artificially added edges as a result of the stego constraints that have been generated. So therefore the one on the bottom is showing what is the CIG of an 8-point DCT after steganography, and the one on the top reflects the CIG of a DCT before steganography. And the same information can be used to regenerate the scheduled and hardware allocated 8-point DCT after implanting steganography, which is on the right side, and the scheduled and allocated graph on the left side shows what is a graph that is available, scheduled graph that is available before you implant the steganography information into that. Also talking a little bit from the security perspective, okay, we can do a security analysis from an attacker's point of view. The maximum possible size of a stego key is given as x log 2 of x, where x represents the total possible encodings of a DSP application and is given by twice or 2 to the power m. Here m indicates the number of operations present in the DFG of a DSP application, and x equals to 2 to the power m also indicates the total number of key-driven hash blocks present in the hash chain. Okay, so that's how we can have the maximum possible size of a stego key. In terms of the attacker's maximum effort of decoding the valid stego constraints, that could be given as twice to the power x log x, because that is the exhaustive possible number of combinations or attempts that an attacker has to make. And the above denotes the attacker's maximum effort in terms of the key security. Okay. Now, besides the key security, the attacker also has to find out the encoded bitstream information that is fed into the twice n number of hash blocks. The total number of encoded bits fed to a hash chain process is therefore given as 1024 minus alpha 1 plus alpha 2 plus alpha 3. But this information on alpha 1, alpha 2, and alpha 3 is unknown to an attacker, and that is multiplied by the number of hash blocks that is part of the hash chaining process. Okay. So alpha 1 would mean the number of bits in the output of the previous hash block that is considered. Alpha 2 would mean the number of bits added before the 380-bit long encoded bit. And alpha 3 would mean the number of bits appended to the 380-bit long encoded bit stream. Okay. So considering all these aspects, the attacker's total effort in terms of finding the encoded bits is therefore given as 2 to the power 100 minus alpha 1 plus alpha 2 plus alpha 3 times the number of hash blocks. And that will be also multiplied with the attacker's effort, okay, of finding the total number of valid stego keys. Okay, so as you can see, that it's a very rigorous effort that an attacker has to make in order to decode the encoded bits and the stego keys. So, in terms of the experimental results, we had analyzed several benchmarks. And the second column shows the number of registers before steganography. The number of constraints is on the third column. So post first phase, we have the PC, which is a probability of coincidence. Post phase 1 and phase 2, as you can see, the probability of coincidence decreases as evident and as obvious, because intuitively, if you keep increasing the number of constraints, either in the same layer or in different layers, the PC value must reduce, and that is exactly what is happening here. And the same thing is done or observed for the stego constraint values for C1, C2, which is 24, 12, 57, 23, and so on. Okay. And in terms of the key size comparison with the related works, okay, we have to also compare with two similar approaches that were recently published. And as you can see, that the IP core steganography approach produces a very strong, robust key size compared to the key sizes of approaches which are published in IEEE Transactions in Consumer Electronics and IEEE Computer Society letters. We've also analyzed the design cost, where we had, we intended to check the overhead of the IP core steganography process in terms of the design latency and area overhead. So as you can see, that based on the effective number of constraints embedded, the design cost of the proposed approach Okay, the IP core steganography approach remains very low, and it is almost zero in most of the cases. And for some benchmarks, for example, in case of JPEG IDCD, MPEG, and EWF, the overhead is minimal and less than 0.5%. Okay, thank you so much, and I hope that I would have been successful in giving you a brief idea of what digital signature and IP core steganography process is all about for securing hardware accelerators. Thank you.
Thank you, Dr. Sengupta. If anybody has any questions, please add them into the Q&A area. Dr. Sengupta will be happy to answer them. We currently don't have any questions in there, but we'll give people a moment to bring them up if they'd like to. It looks to me like you've covered everything and everybody has no questions at the moment. Oh, here we go. Okay. We've got one person who just says, thank you for a good presentation.
Thank you so much.
Yeah, lots of thank yous and good presentations. So it looks like we don't have any questions on this one.
Right. Yeah, I think the audience could feel free to connect to me if they want, even after the lecture is over. So, yeah, I'm open to that.
There actually have been quite a few requests for that. One thing I can tell everybody, if you would like to connect with Dr. Sengupta, on the computer.org website under the Distinguished Visitors Program, his bio is up there, as well as the descriptions of his presentations and his contacts. So you're welcome to go onto computer.org and connect with him. Well, I'd like to take this moment then to thank you, Dr. Sengupta, for your presentation. It was great. I think we all enjoyed it. It had a lot in it. I'd like to thank all of you for your attending this discussion. Our next Distinguished Lecturer webinar series is on the 19th of November at 11 a.m. U.S. Eastern Time on the impact of emergence, nonlinear dynamics, and chaos theory in engineering. Should be an interesting topic. Presented by Chuck Eastham from Chuck Eastham Consulting. We've recently added the Standards webinar series. The first webinar in this series is the Standards for Systems and Software Engineering, What Works. That'll be at 11 o'clock on the 10th of November. Of course, that's U.S. Eastern Time again. And in the Build Your Career webinar series, which focuses on topics such as, softer topics such as taking care of your career and learning how to manage up, that type of thing. The next one will be on the 11th at 11 a.m. U.S. Eastern Time, and it's going to be Stand Out from the Crowd, resumes that will get noticed by employers and interviewing skills to get you hired. And that'll be by Susan K. Kathy Land, the U.S. Department of Defense's Missile Defense Agency. Registration is now open for these, and we'll be sending you a link to these future events along with the slides and the recording of this webinar. Thank you again, and Dr. Sengupta, thank you very much for your presentation.
Thank you so much, Barry. Thank you, everyone. Have a nice day. Thank you so much.
Okay.
Bye-bye.